It's my absolute pleasure to welcome our next speaker, Venkatesh Ramanathan, who will show us now how to scale optimization of graph neural networks. Venkatesh is the Director of Data Science at PayPal, where he leads several applied research initiatives, including machine learning on graphs. As an expert in AI/ML and big data technologies, he has over 25 years experience designing, developing, and leading teams to build scalable server-side software and doing AI/ML research. And he's worked on various problems in the area of anti-spam, phishing detection, and face recognition. Venkatesh holds a PhD in computer science with a specialization in machine learning processing. NLP is really popular. As a fun fact, Venkatesh escaped from Alcatraz this summer in San Francisco's annual triathlon. Congratulations there. All right, Venkatesh, over to you.
Thank you, Adia, for a great introduction. And it's a pleasure to be here. And thank you, O'Reilly, and for inviting me for this Superstream series. It's an honor to be here. As Antya mentioned, I'm just not just a geek. I also participate in triathlon and many events. So this is one of my proudest moment just last month. So I'm very happy with this. So today I'm going to be, the agenda for this talk is about, I will motivate the talk on why we are specifically working on this particular problem and some of the challenges an industry like a financial industry like PayPal is facing in applying some of these latest emerging machine learning techniques to our problem. I'll also give you a brief introduction of graph-based machine learning, which is actually an emerging area in the machine learning and incredibly popular, and also a lot of research is going into this space. And then talk about how do we scale one specific implementation of graph machine learning to one of the problems we've worked on, and share some experiments which basically apply to some large data set and what are some of the early results from some of those experiments. I'll share those on what we can disclose to the audience, and I'll conclude the talk for what we are thinking about in the future. And after this talk, there will be a breakout room where I'll be happy to answer any questions about this talk or in general best practices around financial industry in general. So thank you for joining today. So graphs are actually a very powerful structure for some variety of problems, right? The underlying the fraud and the abuse, that the bad guys don't operate in isolation. So they always have a form of network, and you try to catch one bad guy and they spread the network to the other parts of the network and move around between IP addresses and homes and other geolocations. Fraudsters are constantly moving from one place to the other place, and they are actually not colluding with a group of other fraudsters to basically steal money from a company like us, right? What is actually the fundamental structure representing this is a graph is a very powerful structure to capture those how are they operating today, and how can we actually build solutions to defend and protect industry and also provide better services to our customers. It's also a very abstract structure. It can be also used for recommendations, right? So when we're watching Netflix movies or Amazon recommendations, the underlying structure, if it is represented as a graph, you can build more powerful recommendation solutions. Marketing is another use case, right? So for example, we get influenced by our friends. How can we capture some of these, our friend network as a social graph? And this can be used to actually enable marketing of a new product adoption in your company, which you are working on similar kind of problems like that. So it's a structure which is actually agnostic to a lot of applications in general. But the traditional approaches to applying some of these graph-based techniques is used how the machine learning originally evolved is using feature engineering approach. So you build some manual features. So there is a human involved in coming up with some of these features. So some of the features which are specific to graph in general is like PageRank is, right? PageRank is actually a well-known established measurement where the Google made Google successful in search engine optimization. There are centrality measures, like for example, the degree of a node, which tells you actually how many neighbors or how many nodes which are connected to a given node. That represents a degree. Then you have in degree and out degree, depending upon whether there are how many incoming edges there are and how many outgoing edges. Those actually goes into as features in your downstream machine learning application. So this requires a lot of domain expertise, and that can be used for basically building your machine learning model. That's because the traditional machine learning model uses feature-based approach, right? So you have features and tags, and which are actually column vectors, and these graph-based machine learning used as additional features in your machine learning application to supply graph intelligence to the underlying downstream application. There are also dimensional addition techniques like SVD, intrinsic decomposition, cofactorization, debug, and all the stuff. So, but even though they are also using simpler models like linear models, it doesn't capture the nonlinearity present in your inherently present in the data. So the emergence of deep learning, which is actually coming to the graph-based area, is called graph-based machine learning, is to allow end-to-end machine learning, which means that you can directly go from raw data directly to the models using a learning algorithm rather than having human in the middle to engineer some of these features which I talked about in this slide. So graph embedding actually is one of the most powerful concepts. So it's basically is using graph neural networks to it's got significant promise in the, I will briefly talk about what these underlying graph neural networks is. It's basically extending the traditional neural network which made the deep learning successful to the graph structure. And there are several applications of graph neural networks. You can do a node classification. For example, a node in a graph, you can say whether it's a bad guy or a good guy, right? So that's one simple node-based classification. You can do a link prediction, which basically tells you that there should be an edge between a pairs of nodes. So that can be used for recommendation or product referral and marketing and other applications. Or you can classify the entire subgraph or graph as one thing. For example, group of fraudsters is actually, this is actually an AML network, right? That's another graph-based classification. You can do some of these techniques using graph-based neural network. We have made significant progress internally within PayPal to bringing some of the node-based embedding to production. I will share more in detail about it in the breakout session or in the subsequent presentation. So the current, there are several advancements. This is actually, I say, it's a growing area in the graph neural networks. The current embedding to come up with some of the future vector representation for each node doesn't take into account the hierarchical structure present in data. So actually data is, especially in our financial data, it's inherently hierarchical. For example, let's say you think of individual users and accounts, right? So they do various types of activities. For example, you log into the system, you update your profile, you're making some payment transactions. So all these are granular events which make up your account profile, right? Each user's account profile. And these accounts are actually, again, could be classified, for example, consumers and merchants, right? There are different types of behavior, but it's a type of account, right? So in another hierarchy. Within consumer type of accounts, you could have a bad guy and good guy, and all these bad guys are several, what we call it, restricted, so versus unrestricted. So the accounts could be restricted for a variety of reasons. For example, we have like over 200 plus restriction types. For example, you haven't submitted some of your documents to verify whether your identity is still you, something which you own. So like, for example, supplying some, especially around the merchant verification scenario where you need to supply some tax documents and other information, right? So so the account could be restricted because we're waiting on some documents. Our account could be restricted because we suspect there is some fraudulent activity happening in this. So it could be like it could be you doing the fraudulent activity, or it could be like somebody else took over your account, right? There is several. Again, there is a different classification. So all this you can think of it as a hierarchical classification. And how can the traditional GCN doesn't take into account this hierarchical structure? So in this particular research is that some of the challenges. So I would briefly explain what are some of the challenges specific to financial industry in terms of fraud and abuse. We all know that it's highly complex, and also less than 1% of the transactions are fraudulent, right? So it's actually a needle in a haystack problem. Obtaining ground truth is always a challenge, right? So for example, fraud, one of the thing is that when you look at an image, you can tell whether it's a flower or a dog or a cat, right? So, but the fraudulent transactions is not something which you can, there is obtaining ground truth is not readily available. So you might file for a chargeback, and eventually, you might file a chargeback, but maybe you will look at your statement at the end of the month. After that, you may not have or suspect some fraudulent activity in your account. You might talk to the company, and they might look back and all the past transactions. Before actually we verify whether the transaction is indeed fraudulent, right? It takes time. Right, so that means the obtaining ground truth for fraudulent transactions is time consuming. The other thing is that graph data is not readily available. For example, often requires construction of graph data. From most of the data comes in like event stream. It is stored in traditional relational store. So the graph is not readily available before you can apply graph-based algorithms. So that is another challenge with most of the industries dealing with the graph data. So the other thing is scaling graph algorithms are significantly much more complex than scaling non-graph-based algorithms. So it requires re-architecture from the ground up. So those are some of the challenges. And graph-based, next I will briefly go over how graph-based machine learning, which is specifically graph convolutional neural network, is going to help with some of this task of scaling and building up models which require less human intervention, building up end-to-end solutions, right? GCN is actually one of the, for people who are not familiar with this, most successful technique. It's inspired from the success of deep learning in the traditional domain. When I say traditional domain, where in unstructured data space, where it has been significant promise to industries dealing with structured data like us, right? So the graph neural network is how can we adopt a traditional neural network to a graph-based structure. That's I see that it has gone. You can see from the graph below that it has gone significant promise not only in the research but also in the industry is adopting graph-based techniques there. So how this works, I will briefly explain so that you have some intuition behind how this technique works. Essentially, that a node represents some node is some representation of neighbors the nodes are connected to. So how do you, the neighbors are, whether if there is an edge between you and your neighbors, or for example, you and your friends, and your friend is actually, you are a kind of an aggregation or approximation of who you are communicating with in your social graph, right? The same thing could be thought of as who you are sending payments to and from, or who you are sending money and who you're shopping products with, right? So you can approximate some of your neighborhood information to represent what are you actually, to describe something about you as a node. You can approximate based on capturing neighborhood information. So what you do is that the graph GCN works basically on the underlying philosophy of using something called a message passing paradigm. So each one of the neighboring nodes passes messages to this node, the nodes of interest. So what it passes basically is a feature vector. So you can think of, I know the classical algorithm in the graph is something called label propagation, where the label is passed using message passing paradigm to the nodes of target interest from the neighboring nodes. In the graph-based convolutional neural network, you pass the entire feature vector rather than just a label, right? So it's actually much more broader application for end user building end-to-end ML application. So each node, the neighboring nodes, passes this current feature vector, and each nodes of interest approximated, basically aggregates those information with some kind of aggregation function. For example, you can compute the mean of the feature vector and aggregate those information and average them. That then once you get the aggregate, you pass it through a nonlinear neural network. So this is actually the nonlinearity not present in the traditional model. So the nonlinearity capture more complex interactions which happens between neighboring nodes in your, or even nodes which are which are actually 3 and 4 hops away, right? So how do you approximate some of this information for a given node? Is GCN captures that. So the nonlinearity comes from the neural network implementation, and the averaging of the neighbors is what it approximates, summarize the approximation of some of your neighbors, right? So this is actually a multi-layer GCN. So you can think of it as the first layer of GCN. You approximate your neighbors, then pass it through a nonlinear neural network, like some kind of activation function, like a ReLU, right? Then that becomes the input to the next layer of GCN. You repeat it as depending upon how many ever layers of GCN you are trying to build, right? This level of successively passing some of the nonlinearity through many layers of nonlinearity, it captures much more complex interaction, which is widely present in the how our bad guys, right, move from network to node to node, or some of these complex money laundering movements can be captured through these GCN techniques. So as I mentioned, that the traditional GCN is not applicable to the hierarchical data which is inherently present in. So one of the emerging area in this is something called a hierarchical GCN. So this is actually a research done by Uwe Leskovich group at Stanford. So we try to use whatever the state of the art available in the academia, try to bring it to the industry sooner. So this particular approach is basically what it does is it takes into account the hierarchical structure. So the next slide actually, this picture actually better explains what this technique is about. One of the fundamental problems, there are two fundamental problems. One is actually capturing the hierarchical structure. The second problem is scaling to large, any graph algorithms, including GCN for large graph data is still a challenge, right? So this particular algorithm, the way it works is in the first layer, you capture some of this granular data. For example, in our case, is the event level stream where they're logging into the system, updating the profile. Those events forms as an input to the first layer of the GCN. You use these, you apply one layer of GCN to come up with groups of these accounts which are closely related. So you can think of it as it's basically the idea comes from the clustering algorithm, right? So in this case, for example, you have like nodes of, let's say maybe there are like hundreds of nodes or millions of nodes, and you come up with a much smaller number of clusters at the end of the first layer of GCN. So in this case, there are only 5 clusters, right, identified by the first layer of GCN. So obviously, this is actually a parameter which still you need human. So human has to say how many clusters we think it is there in this particular data. So for example, in our case, we have 200 types of restriction types. So we could use that as a kind of a way to seed into, we think that there are 200 clusters available in this particular data, right? So you can use that as a kind of a guiding point to determine how many clusters are there in this data which we have. So what we have is that at each layer, you are dealing with a much smaller graph during because of the hierarchical GCN, which means that you can, so in the second layer, these clusters form the input to the next layer of GCN. They again apply nonlinearity and neural network to come up with the next hidden layer, then pass it through a subsequent layer. And finally, what you are coming up with a much smaller graph-based techniques. So you're dealing with a much smaller graph at each iteration of the graph. So what the power of this particular technique is not only that you can scale it to a much bigger graph, because of that at each layer you're dealing with a much smaller graph. So we are dealing with a trillion scale graph, right? So you can we can scale it to this, but also capture the hierarchical this things that you don't want to aggregate information about all your neighbors, right? So let's say that the bad guys are connected to the good guys too, right? Or they are pretending to, like for example, they are doing some dual role of, let's say, merchant could be selling good products to some users and, doing money laundering movement in behind the scene for some other type of activities, right? So how do you capture some of this mixed scenarios? And also, you may not share all your information with your friends, right? You may like something about your friend. Maybe you might trust financial advice from one friend, and maybe you want to play or any kind of athletics with some other friend, right? So you don't want to aggregate all your neighbors to represent something about you, right? So you want to actually only aggregate the ones which are make sense, right? So the hierarchical network actually provides applying these clustering algorithms by grouping similar accounts together, then applying GCNs or subsequent layers provides much more powerful in that sense compared to the traditional GCN. So I hope you understand the intuition that I want to make sure that the intuitivity really is clear from these things. So this power is you can apply to your problems, see whether it's useful. As I said, there are several pros and cons. I already elaborated, learns hierarchical structure, and you can you can classify the entire subgraph. Like, for example, you can say that this is actually AML network, right? Or which is actually a subgraph in your original graph, right? You can classify the whole subgraph as a decision making, right? So those are all some of the powerful ideas of GCN. So we try to apply this GCN, hierarchical GCN, in this approach. So scaling, I want to spend some time thinking about scaling, right? So one other thing I alluded to in the earlier part of the talk is that you need to think from look at the entire foundation as a whole. If you want to scale to a much bigger problem or a much bigger scale, I totally agree with Antje and others, Jeff, who said that start small, right? You will hear that message throughout this conference, and I agree with wholeheartedly with that approach. But in order to scale it to a much bigger problem, you need to think of the entire foundation as a whole, right? So you cannot build a solution which doesn't, maybe you are right at the algorithm layer, but if you don't think of what is the underlying foundation on which the algorithm is running, you're not going to scale. You're not going to go too far with your scaling, right? So I believe that the hardware comes obviously at the bottom line. HPC, GPUs and other high performance computing is fundamental critical for scaling graph-based techniques. And I would go ahead and add that it's not just about any general purpose hardware you need. You also, for graph-based algorithms, becoming much more specialized hardware you need to optimize graph-based algorithms and graph-based algorithms to a larger scale, right? The second part is the storage, right? Almost all industries are storing all the data in relational database or in some unstructured data store like Hadoop and Spark ecosystem, right? So you need a specialized graph store to scale graph data to a much bigger scale, like I'm talking about billions and trillions, right? You need to actually also think about where is this data stored. So you can't go too far if you don't have underlying data store which optimizes for graph representation, right? That's another thing. Then all this algorithmic layer comes in, which are actually the whole slew of algorithmic things. We basically employ a lot of open source and also partner, which one of the partners I'm talking about, Intel SIGOPT. I will share some of the experiments I did in this work with this, but there are lots of these partners. You need to find the right partners to partner with so that you can scale your graph algorithms to a bigger scale. Then you build applications on top of this. So message I want to get across is look at the foundation as a whole, not just something in isolation. So basically the way the scaling was done, as I said, that we took this event level data, which is actually, you can think of type of accounts, login, logout, sign up, updating profile, payment, transaction. These are all the individual events used to construct our original graphs. So obviously this graph is actually very dynamic, very granular. So uses data to construct our original graph, then train a hierarchical GCN model to produce our embedding vector from the graph neural network. Then you train a booster classifier. I will tell you why we used to booster classify to do the final end classification, mainly because actually we have extensive rich intelligence from non-graph based intelligence. And our goal is always to beat our champion model. So you cannot, graph can supply part of the intelligence. It can't completely supply all the intelligence. So you need to have feature intelligence from our traditional domains as well. So XGBoost, the boosting algorithm, tries to combine features from non-graph-based algorithms with the graph-based algorithm to build the final classifier, which is basically we are making a decision whether the account should be restricted or non-restricted, right? So one of the fundamental thing where I want to add here is that this is where we think we are closely partnered with Intel SIGOP to do extensive hyperparameter optimization. You cannot build, so there are two parts which I want to emphasize here is one is that you want to scale your algorithm, and also you want to produce a model which are analytically performant, right? There is no point in an algorithm which runs really fast and produces a model which doesn't provide the good analytical value, right? And when I say analytical value, it says that, whatever your KPI, right, or the model is measuring in this case, so if you want to let the bad guy stop the bad guys and let the good guys go, right? So there's some measure to reflect that metric. This is where I think hyperparameter optimization is extremely critical. The traditional hyperparameter optimization available in this open source doesn't have the knowledge or know-how to scale or produce analytical value beyond what our champion models are producing. So this is where SIGOP's hyperparameter optimization significantly helps us in not only scaling but also to produce an analytical value. So I will share the results. So the data set we used for this particular approach is that, as I said, that we Santia was alluding to earlier in the talk, is that we should be start small, right? We started with 3-month data. We went to 15 years worth of data set, mainly because, first of all, graph algorithms, scaling graph algorithms is not complex, but also you want to start small to make sure that you understand it before you can scale it to a bigger this thing. That itself is 33 million. We are dealing with 1 trillion, but for this particular experiment, we used 33 million edges and 10 million vertices. And this is some of the HPC and software which was used to build the experiments. So quickly on the experiment side of things, right? One of the fundamental thing is significantly improve our training time. For example, we resulted in, if you want to do hyperparameter optimization without SIGOP, we were taking like close to 8 hours a day, and this reduced to 4 hours, less than 4 hours, right? So it's 40% reduction in the training time, which means that my research mindset will say that, I want to use this training time to do more, right? So it's not going to be that. So which means that to produce a better model. That's what, when I say more, means to produce more analytical model, right? Which means that it's not it's a training time to build, not a free time to do other tasks, but free time to build better models. That's my research mindset is going. So I used that to build AUC was close to 3% improvement. So AUC actually, I can tell you that AUC is not a measure which is used in a highly unbalanced problem which we are dealing with, but AUC is what the metric we can share. But you can see that I can tell you that internally we were able to beat our champion models using extensive hyperparameter optimization provided by SIGOP. So those are all the summary of the results which I want to share. Finally, to conclude this talk, right? So GCN, as I said, the graph neural networks is a tremendously growing field. Take any top conferences, graph-based neural network is showing significant attention in industry. Sorry, from the academia and the industry, I believe that we should, as an industry, we should adopt some of these emerging techniques which make sense to our problem, right? So one of the fundamental thing where it is helping us is that when we are dealing with lots of these structured data, where the data is stored in relational data store, that's where how can we bring the power of deep neural network to the problems we are dealing with, and also solve some of the specific problems which are inherent in the financial industry, like anti-money laundering, network compliance, and other use cases, which are actually graph-specific task which only a graph structure can capture, right? So, and in this case, I was able to show that a hierarchical GCN shows significant promise compared to a traditional GCN. And hyperparameter optimization using Intel, it not only reduced our training time, but also improves our analytic performance, which is actually extremely critical for us to whether the model goes to deployment or not, right? Next steps is obviously, we are dealing with the multi-class classification, so not just one type of restriction. So even this one was evaluation or restricted to a binary classification, but we are dealing with 200. More than 200 types of restricted accounts, so want to apply to the multi-class classification. The other thing which I want to do, which I really wish I had more time to do that, is that Intel SIGOP provide something called a multi-metric optimization as part of this framework. So which is actually critical, right? For example, we want to let the good guys use our system and let's stop the bad guys from not using the system, right? How do you optimize this jointly using a multi-metric optimization? This is two metrics, right? I can think of an examples where there are more than just two metrics, right? How do you jointly optimize multiple metrics using a single model, right? It's actually an incredible key challenge, and I think SIGOP provides these great functionality. I want to evaluate this for a subsequent talk. Hopefully, in the subsequent session, talks, I'll be able to share some other results with it. But certainly, please check it out. So that is also another thing I would highly recommend. The other thing which I didn't use is an orchestration, which an end-to-end orchestration of the ML pipeline, which SIGOP provides as well. Didn't have a chance mainly because we are an established company. There are lots of these in-house infrastructure, and how do you integrate completely end-to-end pipeline into existing is always a challenge with any companies which have been there. But if you're a new company, you're starting out, it's a great tool to do orchestrate your entire pipeline and scale to much bigger data sets. Promise of this to scale to a trillion scale graph is our next task. So last, I want to add sincere thanks to Andrew Ellingwood from Intel and Edwin Mattia, who's been our great partners to work with in this particular research, and also moving forward with this particular task. So thank you very much.